Okay, hello AP Calculus students. This is Mr. Gerber, and we are going to take a shot here at trying to prove the Lagrange theorem. Okay, the Lagrange error bound is something that we are looking at in AP Calculus, but we don't actually ever quite get around to proving it. So what I'm going to do in the next 15 minutes or so is take a shot at proving this. I'm going to take a shot at sort of proving it. I'm not going to quite get to the completed proof of this because it gets long and sort of repetitious. But I'm going to get you most of the way there to the point where I think you'll be able to see that just by continued application we can finish this off if we wanted to. So we start by looking at the formula for a Taylor series, okay? And we say that if we've got this function f at x, then we could replace f at x with a polynomial according to this format. We say we've got f at a plus the first derivative at a times x minus a plus the second derivative at a over 2 factorial times x minus a squared, and so on off to infinity. And in doing that, we can replace what might be a fairly ugly function f at x with a nice polynomial. The only downside to this is that the polynomial goes on to infinity, which makes it a little bit awkward to deal with. But what we can do is we can say, well, instead of going off to infinity, maybe I just take some chunk of the polynomial. And I can approximate f at x by using whatever amount of the polynomial I decide to use. So I use what we call an nth degree polynomial to approximate f at x. Okay? And that nth degree polynomial I'm going to call t sub n at x, okay, for Taylor polynomial of the nth degree. And of course, by truncating it here at, in my case, it looks like I've truncated it after 2, but I could truncate it after whatever order I want. By truncating it there, I'm left with a remainder out here. Okay, and this is the part that I would not be including, and I'm going to use the abbreviation r sub n at x to refer to that remainder. Now, remember what the Lagrange error bound says. The Lagrange error bound basically says that there exists a value c somewhere on the closed interval from a to x, where a is where my polynomial is centered, and x is the point I'm trying to approximate. There exists this value c somewhere on that closed interval such that my remainder is going to be exactly equal to the n plus first derivative at this number c over n plus 1 factorial times x minus a to the n plus 1. Okay? And so the Lagrange error bound, the Lagrange theorem says, or the Taylor theorem says, that there exists a number c somewhere between a and x such that if I use that number c in my remainder term, I will get exactly what's left over. The problem is there's no way of finding out what c is. And so what we do in the Lagrange error bound is we choose c to make that derivative as big as it could possibly be, and then we can say that the error by truncating the polynomial to the nth degree will be no worse than that. And we're going to take a shot at proving that today. So the way we're going to prove it is we're going to start by assuming that it's true. Okay, we're going to assume the Lagrange error works, and we're going to look at the first couple of Taylor polynomials and what the remainder would be in using those. And then we're going to use calculus to derive that, to prove that what that error would be is exactly what we get from calculus. So that's the basic process I'm going to try and use. So we're going to start by considering, I think we're going to start with a 0 order. So let's take the 0th order Taylor polynomial. Okay? And what that's going to be, well, that would be, according to our abbreviation up here, t sub 0 at x. And t sub 0 of x, of course, is just the first term in our polynomial. Okay? It's just our f at a from up at the top. So t sub 0 of x is f at a, and r sub 0 of x is what's left over. And r sub 0 of x is just going to be the derivative. The next term would be the first derivative, so that's going to be f prime at some number c times x minus a. Okay? So that's my r0 of x. And again, that's for some c on the closed interval a to x. Okay? And so now what I know is that my actual function, f at x, minus my 0th order polynomial, that's going to be my error. Okay? And that's going to be, in this case, f at x minus f at a, because the 0th order polynomial is f at a in this case, because it's just one term. And that's going to have to equal r sub 0 of x. And that, in turn, is f prime at c times x minus a. Okay? So, haven't done very much yet. All we did was we approximated this Taylor polynomial, or we approximated this function f at x using the first term of the Taylor polynomial, t sub 0 x, and the first term is just f at a. And then we just said that the error, okay, this thing is my error, is going to be the difference between what f at x is and what my first term is, which is f at a, and we abbreviate that to r sub 0 of x, the remainder after 0 terms of x. And we know that that has to equal f prime at c times x minus a. Okay. Now what we're going to do is we're going to do it a second time. And this time, we're going to use a first order Taylor polynomial. And the first order Taylor polynomial, we'll call it t sub 1 of x, would be, of course, f at a plus f prime at a, okay, technically over 1 factorial, which is just 1, times x minus a. That's my first order Taylor polynomial. And we know that my remainder then would be the next term. So that's going to be f double prime at this magic number c that we don't know, but we know exists, over 2 factorial times x minus a squared. Again, for some value c on the closed interval a to x. In other words, from some value c between my center and the value of x that I'm trying to calculate. And again, by subtracting, I get that my error is what f at x is minus what my Taylor polynomial claims it is. And that error has to be f double prime at c over 2 factorial times x minus a quantity squared. Okay, so I've done this process twice. Okay, I took a first order Taylor polynomial and I figured out what the remainder would be by using a first order Taylor polynomial. And then I did a second order Taylor polynomial and I figured out what the remainder would be in using a second order Taylor polynomial. And that's all I've done so far. Okay? All right. Now, we're going to try and prove that this is true. In other words, we're going to use some calculus to see if we can get the same results. And I want to start by asking you to recall the mean value theorem. Okay? You remember the mean value theorem says that if I have a function f, and if f is differentiable on the open interval a to x, then there exists a c on the open interval a to x such that f prime at c equals f at x minus f at a over x minus a. Okay? Oftentimes when we look at the mean value theorem, we use the closed interval ab, but I'm using the closed interval ax in this case because it leads me to where I want to go. But it's the same thing. Okay? Essentially, all we're saying is this. If I have some function that looks like this, and I say that this is the function f at x, and then I evaluate and I get the slope of the secant line from a to x. In other words, I get that slope. Then what I can do is I can say that somewhere there's going to be a point with the same slope, and that value I'm going to call c. Okay? That's just the mean value theorem. We've looked at that already. Okay? And in this case, this gives us that f prime at c equals f at x minus f at a over x minus a. Or another way of saying that would be that f prime at c times x minus a is going to be equal, I'm going to put it on the other side, is going to be equal to f on x minus f at a. Okay? And you remember that f at a, this thing, is the 0th order Taylor polynomial. And that this thing is the remainder if we use a 0th order polynomial. In other words, if we go back to what we just had, what we've got here is f at x, let me just write it down, f at x minus t0 of x equals r0 at x. And if we go back a page, you'll see that that's what we just had. F at x minus t0 at x equals f prime at c times x minus a. So our error rather, when we use a 0th order polynomial, we can actually get that same result without using Lagrange theorem, simply by using the mean value theorem. Okay, so we've sort of confirmed that it works for the first order approximation. Now the trick is, how do we do it for our second order approximation when we wanted to use a first order Taylor polynomial? Well, we're going to do the same sort of thing. We're going to consider the mean value theorem again. Except this time we're going to apply it to the first derivative. So if I think of the first derivative, I've now got a function, maybe it looks like this. But this time I want this to be f prime at x. And I want to go from a to some number x. And I'm going to have the slope of my secant line. And the mean value theorem tells me that there's got to be a tangent line with the same slope there. The only difference is this time it's f prime at x. So now the mean value theorem gives me that f prime at x minus f prime at a over x minus a is equal to f double prime at c, right? For some c on the closed interval a to x. And again, I can rewrite this a little bit, and I'll get f prime at x minus f prime at a equals f double prime at c times x minus a. Now, the problem is that's not giving us what we wanted from our earlier work. If we go back and look at this again, when we did our second approximation here, we ended up with this, f at x minus t1 at x. And so that's what we actually want to get to using this mean value theorem approach. What we want is to end up with f at x minus t1 at x. And so in order to get that, we see that we're kind of close. We're going to need antiderivatives. We're going to need to anti-differentiate this thing. So let's go ahead and do that. If I take the integral, the antiderivative of both sides, I'm going to end up with this. The integral of f prime at x minus f prime at a, we're going to anti-differentiate with respect to x, of course. And that's going to be the integral of f double prime at c times x minus a dx. Okay? Haven't done anything very profound yet. I've just taken integrals of both sides. Now, as I go through this, well, the integral of f prime, the antiderivative of f prime, of course, is just f. And the antiderivative of f prime at a, well, that seems worse than it is because f prime at a is a constant, right? This is the slope at some value a. And so the antiderivative of that is just going to be f prime at a times x. Okay? And now we've got this thing, f double prime at c times x minus a. Well, again, f double prime at c is just a constant. So this is going to be x minus a squared up here. And then I'm going to need a 1/2 of that constant. So there's my antiderivative of that. And then, of course, I need a plus k. I'm going to use k for my constant instead of c because I'm already using c as the value where I'm getting the Lagrange value. Okay, so I don't want to confuse it with additional c's. All right, now to deal with the k, I'm going to say, well, let's let x equal a. Okay, in other words, let's put me right at the center of this approximation. And if I let x equals a, then this equation becomes f at a minus f prime at a times x is going to equal f double prime at c over 2 factorial times, well, you can see here, this is going to be x minus a, but x equals a, so this just becomes 0 squared plus k. And that's nice, because that's going to take that whole thing to 0. And so I'm left with k equals f at a minus f prime at a. Ah, wait a minute, sorry. This x should have been an a because I'm letting x equal a. So k equals f at a minus f prime at a times a. Okay? And now I can substitute that back up into here. And that's going to give me, I've got to go to another page. When I do that substitution, I'm going to be left with f at x minus f prime at a times a no, sorry, f prime at x times x equaling f double prime at c over 2 factorial times x minus a squared plus my k, which is now f at a minus a times f prime at a. Okay, that's a little bit complicated, but if you go back to the previous page and just check, you'll see that that works out. Okay, basically all I've done there is take this value for k and put it in to that k. Okay, and that's the result I've got on the next page. So now we can continue. So where do we go from here? Well, let's isolate this piece right here. So I'm going to pull everything over to the other side. So now I'm going to get f at x minus f prime at a times x minus f at a plus a times f prime at a, and that leaves me with f double prime at c over 2 factorial times x minus a squared. Okay? Now I'm going to group these things together. I'm going to keep the f at x outside, and I'm going to subtract. And what am I going to have? Well, here I've got f prime at a. Let me do this in 2 steps. I don't want to confuse you. So this is just going to be f prime at a times x, and this is now going to be minus f prime at a, minus a times f prime at a, minus that term. And then I must have a plus f at a because I factored out a negative. And that's got to equal f double prime at c over 2 factorial x minus a squared. Now I can start to see where this is going to work out. Okay, in here I want to factor out an f prime at a out of that term, out of those 2 terms. So that's going to leave me with an x minus a. And then I've got plus f at a. And that equals f double prime at c over 2 factorial times x minus a quantity squared. But, and this is the beauty of this, I can recognize that this whole thing is just T1 at x. Is just T1 at x. And so now, what we're left with is f at x minus T1 of x, okay, T1 of x being our first order Taylor approximation to f at x. And that equals f double prime at c over 2 factorial times x minus a squared. And so, if we go back now and just take a look, I'll go back 2 pages. And remember when we considered our first order Taylor polynomial here, well, this is exactly what we ended up with. F at x minus T1 at x equals f double prime at c over 2 factorial times x minus a squared. That's what I just had right here. Okay, this is the same. But in this case, on this page, we got this having nothing to do with Taylor polynomials. We got this just using the mean value theorem applied to the first derivative. So what we find is that the mean value theorem guarantees that the Lagrange error bound holds true if we use a Taylor polynomial of degree 0. And now we also prove that the mean value theorem guarantees that the Lagrange error bound holds true if we use a first order Taylor polynomial. We can repeat this process using increasing degrees of the mean value theorem to get what happens if we use a third degree polynomial and a fourth degree polynomial, and we can eventually prove that it's true for any degree polynomial. I'm going to save that for you to look up on Google or find somebody else who's taken it that far, because the anti-differentiation gets a little bit uglier as you go forward. But I think we've got enough now that you can see that the Lagrange error bound does hold true. We've derived it twice for two different Taylor polynomials using nothing but the mean value theorem, which we had already known from our studies in calculus. So I hope that this helps to clarify a little bit about where this comes from. It's a beautiful theorem, and we'll be looking at some examples in class tomorrow.